Well, hello there. Welcome to this video. My name is Craig Hane, and my students call me Dr. Dell. And you can learn all about me at my website, craighane.com. And this is going to be a story about Galileo and how he batted 50% in this story, which will make sense in a moment. And this is a story that I tell my students that are taking Tier 5 on calculus in my 10-tier program, which I describe in great detail in my book, Teaching Math, which you can get a copy of for free at our website at craighane.com. Now, the reason I say Galileo bats 50% is I'm going to tell you two stories. One he was correct in and one he was wrong in. And the first one is about the trajectory of a ball. And I'm going to do this the way we do the notes in our calculus training in Tier 5. So you may want to download a set of these notes, which you can have for free if you just simply go to craighane.com/Galileo. Now, the facts are Galileo believed that if you threw a ball, it would follow a parabolic trajectory. And indeed, it turned out he was correct. But this contradicted what Aristotle thought. The great Greek Aristotle thought the trajectory of this ball would be a circle. And of course, a parabola and a circle are not the same thing. And so what I thought we would do is just look at the two and see what the trajectory really is and why it wasn't the circle that Aristotle thought. A parabola that we're going to consider has an equation y equals 1 minus x squared, and the circle we're going to consider has the equation 1 minus x squared square root. Now, first thing we want to do is we want to graph both of these on the same axis, and so we're going to use Wolfram Alpha to do this, and this is the instruction that we give to Wolfram Alpha, and if you've downloaded these notes, you should type this in yourself into Wolfram Alpha and see what the results look like. Okay, we went to wolframalpha.com and we typed in the instruction that was the same as here. I just copied it into Wolfram Alpha, and it plotted both of these curves. This was the parabola, this was the circle, and there they are. And we see here is the parabola, and this is the circle, and Wolfram Alpha tells you which is which. And so we can see clearly they're not the same. And so Galileo certainly had a much different understanding of it than Aristotle did. Well, now let's get curious and see what would be the arc length for that parabola. And so we're going to type in this instruction to Wolfram Alpha. The caret symbol means as an exponent symbol. And it'll tell us this is the arc length of this parabola. And here is the formula for the arc length. It does it for us. It shows us the antiderivative if you needed to know it. But it does all that for us. Wolfram Alpha does everything. And here is the trajectory of the parabola, and there is the arc length. Well, the arc length of the parabola was 2.9579, and now let's look at the arc length of the semicircle, and we've typed that into Wolfram Alpha, and it was going to give us that answer right there, because this is what it comes back. Here is, of course, the formula for the arc length of this circle. There is the arc length, and once again, there's a trajectory, and Wolfram Alpha, of course, has done all the heavy lifting. Now, Aristotle probably would have seen this discrepancy from this example because, after all, if you look at this thing here, the trajectories for the circle, this is a vertical tangent here, and he would have known that the tangent would have been like this. So he would have known this was probably not the best example we could have chosen. So can we come up with a better example? Well, I thought about it a little bit, and it seems to me that we just threw the ball too high. Let's say that we decide to throw it, and it's only going to go up 0.5 compared to the total distance it's going to travel with 2. In other words, we want to keep this distance less than half of the total, whereas up above we had the thing going all the way up to 1. Well, in this case, with a little algebra that we learned back in Tier 4, we can quickly see that the equation of the parabola then, for this example, would be 1/2 minus 1/2 x squared, and for the circle, it would be this right here. And so let's plug those into Wolfram Alpha and see what it looks like. Well, as you've learned in calculus, what you always want to do first of all is graph whatever it is the function you're studying. So we're going to graph both the parabola and the circle, or the semicircle, on the same plot. So this is where you plot, this would be the parabola, this would be the circle from -1 to 1. This is the instruction that you put into Wolfram Alpha. If you copy these notes, you can copy it right off of them. And when you plug it into Wolfram Alpha, there it is. It plots these two things for you, and there you see the parabola and the circle plotted now. And don't you see, they look much, much closer. So you can see where Aristotle might have been confused and thinking that the trajectory was a circle in an example like this. But of course he was wrong and Galileo was right. Now, I like to go a little further sometimes. Back in the old days, we could have plotted these two things with a good graphical calculator, just like we did with Wolfram Alpha, but I want to go a step further. I want to know what are the arc lengths of those two trajectories. And so you put this into Wolfram Alpha, and this will give you the arc length of the circle, and this of the parabola. Now, when we look at the arc length of the circle by putting that particular instruction into Wolfram Alpha, it comes back and shows us it's 2.31. Notice, of course, that first you have to put in the formula, or you don't have to. Wolfram Alpha puts in the formula for the arc length. Then it finds the antiderivative and evaluates it. If it couldn't find an antiderivative, by the way, it would just do it numerically. And now we come to the parabola. Wolfram Alpha goes ahead and calculates the arc length of that. But notice what it did here. This is the integral, and this is the definite integral. What would be the antiderivative if you did it the old-fashioned way, and we're doing it manually? Well, you can put in integrate this function here. By the way, this came from the arc length formula for the arc length. And then this would be the antiderivative. And don't you see, that might be a little bit complicated to come up with. It involves a hyperbolic cosine, or hyperbolic sine rather. And so that's the kind of difficulty you get into in the old days. Wolfram Alpha just handles all that up for you. And I just put this in to show you what we don't have to do today that we would have had to in the old days. And Wolfram Alpha now gives us this example. So we see the two arc lengths are very, very close to each other. Well, it appears to me that the lower we toss the ball, the closer these two models will fit. That is, the parabola and the circle. And certainly that was the case here. So Aristotle wasn't too far off in the example we just gave, but nevertheless he was wrong. Now, the truth of the matter is that we've always need to be suspect of any math model of some physical phenomenon. No math model is ever totally accurate, modeling the phenomenon, whatever it is. There's always has to be some kind of simplifying assumptions. For example, if Galileo had not ignored the air resistance, he would have been wrong. Or if he did ignore the rotation of the Earth, he would have been wrong. In other words, he made some simplifying assumptions. Furthermore, it turns out that the more powerful our tools are, mathematically speaking, the better models we can construct. Next, I'm going to give you an example where Galileo thought he had another good model for a phenomenon, but then along came a more powerful tool called calculus. And when it came along, it showed that Galileo was wrong in this second example. Well, the second example is one of a hanging chain dangling between 2 points. And it's called a catenary. That's the curve that it forms. And the question is, what shape does this chain, if it has a uniform density, form when it's hung between two parallel points? Now, Galileo thought it was a parabola. But unlike the trajectory, he didn't have any way to prove it. He was able to actually give a good argument for the trajectory that we just looked at, but he had no way to prove it, so he just guessed at it and thought it looked right. But once calculus was invented, there were several mathematicians who were able to prove that, in fact, it was not a parabola, and it's what is called a catenary today. Now, this shape that's called a catenary is the graph of something called the hyperbolic cosine, which can be defined as e to the x power plus e to the minus x power, all divided by 2. Now, we talk about hyperbolic trig functions, as you know, in calculus, and how they are actually parametrically define a hyperbola, but we won't get into that here. You know what they are. The question then now becomes is, what is the difference between a catenary and a parabola? How far off was Galileo? Well, the facts of the matter are, if you've got a parabola and it goes through the points 0b, a0, and minus a0, it'll have this form. We learned that back in Tier 4 in analytical geometry. And we also know that if we evaluate the hyperbolic cosine at 0 and at 1 and at minus 1, we get these three numbers. You can do that with the TI-30XA calculator. And so what that means is that this equation, y equals 0.543, notice this is 1.543 minus 1, times x squared plus 1. This will be a parabola that passes through the very same 3 points the catenary passes through at these 3 points right here. And so that's something we can learn just from what we already know about the hyperbolic cosine and the parabola from Tier 4. But now the problem is, let's plot these things and let's calculate the arc lengths, and this is where we're going to need Wolfram Alpha. Okay, we're going to use Wolfram Alpha to do something that we really couldn't do manually, I don't think in any practical way. We're going to plot the hyperbolic cosine and that parabola. They all pass through the same 3 points, and we just simply put this into Wolfram Alpha. So if you've got these notes, you can just put this in yourself, and then when you do it, it'll graph both of these things. And here's the hyperbolic cosine and the parabola graphed together, and in fact they're so close it's hard to even tell them apart. So it's quite understandable why Galileo thought it was a parabola, But in point of fact, it's not a parabola. They have slightly different arc lengths, and there is a measurable distance between them, as we'll soon learn, again using Wolfram Alpha. Okay, this is something normally you wouldn't do if you had to do it the manual way. It'd just be way too much work. But we're going to plot the arc length, first of all, of the catenary from -1 to 1, and then of the parabola from -1 to 1. And what we're going to see is that it's 2.35 versus 2.34. So they're very, very close to each other, as we knew they were. And indeed, this is what they look like on Wolfram Alpha. This would be the arc length of the catenary. And there it shows right there, there's its arc length, and it shows what it is. This would be the formula for it if you apply the arc length formula. And then here is the one for the parabola. And once again, very similar shape, and it's 2.234. So slightly different. And so now, by using Wolfram Alpha very quickly and easily, we can see that the two arc lengths of these are slightly different. Now, as you learn in the calculus training, Wolfram Alpha makes things so easy. You just ask a lot of questions you probably normally wouldn't ask if you had to do it manually. I'd like to know what is the difference in area between these two curves, the catenary and the parabola. So we integrated the difference in the two curves from 0 to 1. Indeed, there is the answer, and it's 0.01. So that's how close together they are. And that certainly explains why Galileo was wrong in his thinking and how he could easily be misled. Okay, I hope you enjoyed this little exercise. It was a lot of fun for me to do it. It took me a couple hours to put this together. And I did it for the calculus students that are taking our Tier 5 calculus. And I believe there's several lessons we can learn from this. First of all, no matter how good a math model you've got, no matter how close it seems to fit, it's never going to be perfect. There's always going to be a better one. And secondly, if you've got a tool like Wolfram Alpha, then you can start exploring these models today in ways you never could do with the old, time-consuming, and difficult classical techniques that are taught even today in most calculus courses. And just how great were our ancestors. Aristotle, he's considered to be the father of modern logical reasoning, Aristotelian logic. Galileo is considered to be the father of modern science. But of course they made mistakes given the tools they had to work with. Along came Newton and Leibniz. They were able to correct Galileo on the catenary because they had the tool of calculus. And as a matter of fact, Newton went ahead and created a math model for physics, which is used even to this day for what I would call standard ordinary engineering. However, you couldn't do something like a global positioning system, GPS, today with Newton's model. Newton's model was replaced by a more accurate model by Einstein in the early 20th century. Then Einstein's models don't even work in the nano world. Then later on in the 20th century, we had quantum theory. And these math models just keep evolving and evolving, and every model gets replaced by a more advanced model. I don't know that we're ever going to come to an end of this, certainly not probably in our lifetimes. I believe that it behooves any of you STEM students to keep up to date on the very latest tools. And a great place to begin is to learn calculus and differential equations using a tool like Wolfram Alpha. Of course, it's free, and it's what I use in the Tier 5 where we teach calculus. And we do this then in a very new, revolutionary way, quite different from the standard courses taught today. As you very well know, we do not use the old 19th century epsilon delta arguments that are used to try to put some rigor in. We use modern infinitesimal arguments, which have been very valid since the 1960s. And of course, we don't use the old techniques of integration, which are essentially obsolete today. They've been replaced by Wolfram Alpha. In fact, the facts are today, any student can learn all the concepts of calculus and need to solve any calculus problem or differential equations that are going to arise in any STEM subject much quicker and easier than any classical course. In fact, you can go through our calculus course usually in about one semester. More importantly now, you can solve problems that you couldn't even attempt them with classical calculus. I mean, it's just amazing what you can do now. And you can learn the concepts so much better because you get to see so many more examples and graphs. It's just, you have to experience it to believe it. In fact, Wolfram Alpha does for the classical tools of calculus that are still being taught what the scientific calculator did for the slide rule and for log and trig tables back in pre-calculus about 40 years ago. So you want to get with the times, learn to use Wolfram Alpha, learn to do calculus the modern way. And this is Dr. Dale. You come to my website, you can download these notes for free, learn all about our 10-tier program and how we do it. And who knows, maybe we'll get together at some point in the future. I wish you the very best in your future career as you pursue, hopefully, a STEM career.